So welcome to a little crash course here. We're going to be doing f double prime and what it tells us about f. So before we begin, I think there are two basic concepts we need to kind of talk about, and that is what is a double derivative, which is f double prime, and what is an inflection point. Okay, so a basic calculus concept is a derivative, which is, let's say we're given f of x equals 3x squared. The derivative of that, we use our basic power rules, and we'd find that f prime of x would be equal to 6x. Now, a double derivative, as the name implies, is kind of the same thing. You're taking the derivative of f prime one more time, which is essentially taking the derivative of f here two times. So f double prime of x in this context would be the constant rule, which is going to be 6. So that's just essentially taking the derivative of this twice. As you can see, we go from f of x to f prime of x to f double prime of x. And that's just basically what that is. Now, our second big concept here is going to be our inflection point. But to kind of talk about that, I need to start talking about concavity first. So here we have a nice little cycle of sine going on right here. We can divide this in half, because as you will notice, there are two kinds of concavity going here. There is concave down right here, and concave up over here. Now you're wondering right now, what does that mean? Well, concave down, concavity is basically the way that a graph opens up at a specific given interval. So if you notice right here, this is upside down and it's opening downwards. And a good way to remember concave down is concave down kind of rhymes with frown. So if you were to draw a full cycle, if you just continue over here, this looks like a frowny face. So concave down is kind of like frown. That's a good way to remember it. There we go. Sorry, my handwriting is kind of messy, but. And on this side right here, you have concave up, and it's kind of like a cup, if anything. Because if you imagine you pouring water in here, you would fill it up kind of like a cup. This part's concave up, and you remember that by the cup. So if you'll notice, you're going concave down, concave down, concave down, concave down, concave down, and then concave up. So at this point right here, we're changing concavity. And that's going to be our inflection point right here, where we change concavity. And put I inflection point. So inflection point is anywhere on a graph where that graph changes concavity. And that point right here, we're going to have it at 0, 0. So now that we're kind of done with that, let's kind of say, what does this all mean in the context of the AP exam in terms of the problems that may be given there. So let's say that they give us a problem, I'll start with something, just do something simple just to get the concept down, where f of x is equal to x cubed plus x squared plus x. Let's see if you see that. Yeah, we can see that pretty well. Okay. So let's say we're given this and we're told to find where it is an inflection point. So if you notice, we graphically represent this as the point where the graph changes concavity. Now, if you're not given a graph or a visual and you don't really have time to draw that or anything, it's like, how would you go about finding that? So the first thing you're going to do, as we talked about earlier, is find your second derivative, or your second derivative test. So it's just going to involve taking the derivative of this twice, which is pretty simple to do. So f prime of x is power rule 3, x bringing it down to power squared, plus 2x, and that's just going to be plus 1. So our first derivative, second derivative, same old, 6x plus 2, and that 1 goes away because that's a constant rule. So we're left with 6x plus 2. Now if you notice something, we can always factor out a 2, because as we learned from Algebra 2 and Pre-Cal, that we really can't do anything with this in this form. So we're going to pull this 2 out right here, and then get our 3x plus 1. Now to get an inflection point, you're going to set your x equal to 0, just like kind of finding a solution to a root. As you notice, the x right here is always going to be equal to 0. So if you were to take this 2, there's no constant out here, so we can kind of disregard this 2. So 3x plus 1 equals 0. We have our 3x, if we subtract our 1 here, minus 1, equals negative 1. We just divide this by 3, all this whole thing by 3. And we get x equals to negative 1 over 3. So this right here, this is going to be our inflection point, because that's where we set our whole second derivative equal to 0. So that's our IP, short for inflection point. So let's say we were to take this one step further and we were to kind of try to figure out which side is concave up, which side is concave down. So we do our second derivative test here, which is basically where we kind of try to chart this out on a number line. So we have our x equals 1/3 right here, or negative 1/3 rather. And so what we're going to do with this is we're going to take a point, arbitrary point from the left-hand side and from the right-hand side. And if this point here, our f double prime at this point, of C, as we'll call it, is greater than 0, then we're going to know if it's going to be concave up. our little cup is going to be opening upwards, as that U is. And we know that if our f double prime of c, as you're going to call it, is less than 0, that it's going to be concave down. And so, as I want to kind of go back and reiterate, this is a potential inflection point. We're not exactly sure yet because we don't know if it changes concavity yet. So that's kind of what we're trying to determine here. So for negative 1/3, I'm going to pick negative 2, and you're going to plug that back into your x. So negative 2, no, I'm sorry, your f double prime of x. So 6 times negative 2 plus 2. We're simply given negative 12 plus 2 basic math. That's going to be negative 10. So we know that this whole portion right here is going to be negative, which we know that this is going to be concave down on this interval. So if we pick a point that's larger, let's just, for the sake of simplicity, go with 2. 6 times 2 plus 2 is going to be 12 plus 2 is going to be 14 basic math. So when this is a positive number, this is greater than 0 set here, so it's going to be concave up for here. So now that we find that this is indeed an inflection point, because we're going from negative to positive here at this point, just kind of as we're going from concave down to concave up at this point. So that's how we know this is no longer a potential inflection point, it is in fact an inflection point. So that's our second derivative test. And that's how we determine both concavity and our inflection points from f double prime of x, and we describe f of x. Okay?